Hello, fellow physics enthusiasts. Well, today I am going to be providing a little bit of a demonstration about how to derive the three equations of motion analytically. Now, this is going to be a two-part series where I derive them analytically without the use of calculus, and then I will demonstrate how to go about using calculus to show you that there's more than one way to skin a horse, so to speak. So, as you can see, we have three equations right here with no prior context, and I'm going to try to expand on these and go one by one for all these cases. So, starting. So first I would like to begin by drawing out a velocity versus time diagram. And through doing so, we can analyze that and then derive Newton's first law of motion, first equation of motion, I might add. Now, how can we express that? Well, here we have our... So we have our axis, where our horizontal axis is going to take on our time and represented in units of seconds. Then our vertical axis will simply just be our velocity, and the units there will just be meters per second. Okay, so what I want to express first and foremost is a body moving in a constant velocity over an elapsed amount of time. And how can we express that on this diagram? Well, it's quite simple. All you really need to do is draw out a horizontal line and just allow it to remain constant. Now, what does it mean for an object to remain at a constant velocity? Well, that simply just means the velocity is unchanging. It remains constant throughout its entire trajectory. So if this began at, we'll say, 5 meters per second, it will remain 5 meters per second for the entire elapsed amount of time. And this is a representation of a body in motion that isn't accelerating. Well, how can we express a body in motion that is accelerating? Well, by definition, acceleration is just the change in velocity per unit time. Now, let's illustrate that here. And we'll start at some initial condition where our velocity, we'll say, is right here at some arbitrary value. So our acceleration now will be represented in terms of a slope moving upward here on the graph. And that is expressing the change in velocity per unit time. Now, how can we go about expressing an equation to fit this graph? Well, as we can see here, we have our initial velocity represented in notation of v naught. That's what that little circle is. Well, now our elapsed amount of time will keep going until we reach the region at which we want to measure. So at this point, our velocity is what our equation is going to be in terms of. So we can express that by simply writing out our final velocity, or v sub x, equals our initial condition for velocity plus the product of our acceleration and our time, as so. Now, the way I like to go about this is thinking about it in terms of, if any of you who have taken some beginner level math courses might understand the slope-intercept form. Well, we have y is equal to mx plus b, right? So b is generally denoted along the y-intercept. That will just be our initial velocity. That is analogous to our initial velocity. M being our slope, in other words, the acceleration, x being time, since this is along the x-axis, and y being our final velocity. So now that we got that out of the way, we can go on to express our second equation of motion, since we have number one right here. So using the same graph, we can express our second equation of motion that I showed earlier. So what is our second equation of motion? Well, the best way to think about that is in terms of the average velocity of our object in motion here. So our average velocity will simply just be split down the middle. We're going to have some average velocity where this is cut in half. Now what does that mean? Well, we're splitting the area under this curve. Now, what is the area? Well, based on this representation, the area is simply just the total position covered on its trajectory through its motion. So I'm going to shade in this region. Right here is our area beneath this curve, and that is equivalent to our distance traveled. Well, we can represent this average velocity like so. Well, we're going to be basically using the same equation, except with a little bit of a different value. So V average will be equal to the same initial velocity point we had earlier, V naught, plus, well, now we've cut our distance in half, our slope in half, I should say. This value will now be 1/2 AT. Now this isn't the equation. We first need to define what velocity average is. And as I mentioned before, the average underneath the curve represents the total distance covered. So we're going to have V average equal to some final position minus some initial position over the elapsed amount of time. Now what we can do here is just plug in this value to our equation, and we're going to have x minus x naught over t equals v naught plus 1/2 AT. Now we can just manipulate this just a little bit to simplify it, bring that t over, and I'm going to apply a Greek notation as I showed earlier to represent the change in. So the change in position is equal to this time being distributed over to the other side, which will simply just be v naught t plus 1/2 AT squared. And there we have it. We have our second equation of motion. And now to derive our third equation of motion. Now this requires a little bit less analyzing the graph and more arithmetic. Now there's two ways you can do it, and I suggest, in terms of simplicity, you can use both of these equations to verify what this third equation is. Now this third equation is a little bit different. It's still using a constant acceleration, but the main difference is the fact that it is a time-independent equation. Now when you're going through some of your problems, you may be absent of time in terms of what variables you have at your disposal. So it's very useful to have an equation that removes that need for time, figuratively speaking. But how can we go about this? Well, using these two equations, you can rearrange this velocity, this first velocity with a constant acceleration, in terms of time. And we will do that. So let's rearrange it here to where we have t. Marker here. So we're going to have t equal to v final minus v initial. Divide that by, almost did t there, divide that by acceleration. So we have this. Now what we could do is just plug this value into that equation and then just rearrange it. It gets a little messy, so I don't recommend it. So the best way to go about it is to just know the area of what this shape is, a trapezium. So what is that? So the area of a trapezium is simply equal to 1/2 base, so our base here, times our height of 1, our first height, I should say, plus our second height. And from there, we can begin to fill in the variables that these ones are representing in our diagram. So what will that be? Well, our area, as we just verified before, is simply just our change in position. So we can replace our change in position with A here. So delta x is equal to 1/2. And what is the base? We have our base here along the x-axis of time, the elapsed amount of time. So we'll just replace t for b there. We're going to have t and multiply that by our two heights. So what are our two heights? So let's see. Our first one we can see is the height it takes to reach this point right here, our initial velocity. So h1 is simply our initial velocity. So let's plug that in here. And what is our second height? Well, our second height is the distance from here to here, which is our final velocity. So we have final velocity here. So we'll just plug that in for h2. Now I'm going to represent that by v sub x. So now, this makes things a little more simple, algebraically that is. So we're going to plug what we just rearranged over here in for this equation and go from there. So let's try to maximize some of my space here. So delta x will be equal to 1/2. So plugging in for t, we're going to have v sub x minus v naught over our acceleration. And that'll be multiplied by what we just had for our two heights. So v naught plus v sub x. And now we can just kind of start algebraically simplifying this. So see, we have our two sets of variables here for our velocities. We can just represent that by delta x is equal to 1/2. V sub x times v sub x is final velocity squared. And then multiplying our initial velocities will be minus v naught squared over a. And now we can just rearrange our equation, and that will give us v sub x squared is equal to so that will be equal to v naught squared plus 2a delta x. And there we have it, our third equation of motion. And this is, in my opinion, one of the most intuitive ways of expressing this algebraically and analytically. So the following video will just be expressing how to go about this using calculus as opposed to this analytical method. So stay tuned, and I will have another version coming out.